finish 3 questions, right, for today in probability. Then after that we'll move into chapter 3 where we are going to look at cumulative frequency distribution. Okay. So 2.4. Sorry, did I do question 2? I didn't go through the parts, right? Question 2, part I. Is it question 2 for practice now 10? Go through our answers. Right, in part I, we want to find the probability that the first ball is red and the second ball is blue. What would that probability be equals to, Joshua? 7/30. How do you get that? 8/16 times 7/15, so we should be getting 7/30. Right? Next, in part 2, we want to get one ball is red while the other ball is blue. Okay? So, one red, the other blue. Okay? What would the answer be then? Ding Hui, what's your answer? How do you get 7/15? 8/16 times 7/15 plus
7/16 times 8.
Okay, great. So one red, the other blue, so it's either red blue or blue red. Okay, so there are 2 cases to consider. And then lastly, we want such that 2 balls are of the same color. So what's your answer? 40. 33/40. Okay. How do you get 33/40? Okay. Do we get this answer? 33/40? I got 49/120, right? So answer, could you please check? He might have keyed in the calculator wrongly. Yeah. Should be 49/120, right? You get it? Okay. Next, I want us to look at exercise 2C, question 15. Okay. This question a bit slightly complicated. There are 2 boxes, box A and box B. Box A has 7 blue and 5 yellow. Box B has 3 blue and 7 yellow. Okay, so one ball is removed at random from box A and placed into box B. Okay, and after thoroughly mixing the balls, a ball is drawn at random from box B and then placed into box A. So is from box A to box B. Second step is from box B to box A. Okay, we want to draw a tree diagram to illustrate the experiment. Okay, so how will this tree diagram actually look like? Could I erase the previous questions already? So we are first considering box A, where there is a blue or yellow marble, is it? Or ball, okay? Then, so the chance of picking a blue ball, okay, is 7 out of a total of 12, and picking a yellow ball is 5 out of 12. Okay? Then we transfer it into box B, right? Okay, so this is taking from box A. Okay, so then we move on to box B. Let me just adjust this. I don't think there's enough space. We also have blue or yellow. Okay, but what will the probability be like? So if we had taken a blue ball, okay, from box A and placed it into box B, what do you think would be the total number of balls found inside box B? Yes. Noi? 7? 7 what? What's the total number of balls that are going to be found in box B? After I take one from A to put into B. There will be 11, right? Okay. So originally there's 10, now we have 11. So we need to be clear about total number first. Right? If I had taken the blue one and placed it into box B, what do you think is the probability going to be over here? Nicole, what do you think? If I take one that's blue and I put it into box B, now I'm taking one out of box B. How many blue balls will there be in the box now? In box B? You understand the context of the question? 6. Why 6 then? Yes, come here, don't need to do that. Why 6? Where does 6 come from? I take one blue one from box A, put inside box B. How many blue are there in box B now? 4, right? Okay, because originally that's 3, we now have 4 blue ones, okay, in box B. Okay, then how many yellows are there in box B if I had taken a blue one? How many yellows would I have? 7, right? Okay, then what is the probability for the remaining 2 branches going to be? Chloe? For this one? 3 out of 11. And the last one? 8 out of 11. Okay. Now, is that all? This is not all of the tree diagram, right? Because we are only considering taking from box A and then put it here. Taking from, now we have not yet moving from taking from box B. Hang on now. Box A, go to box B. And now I'm so a bit off. How's the procedure like? Take from box A is this probability I put inside here. Now I haven't taken from box B yet, right? To put back into box A. Should I rephrase this thing here? take from box A to box B. Any suggestion on how we could better phrase this? Take from box A to box B. Take from box. Take from box A to B. From A to B. Take from box B, right, to put to A. You understand what I'm confused about, right? But I'm not adding it here. Because this is the probability of taking from box A to put inside box B. Then this is the probability of taking from box B to A. So there should be 3 sets, and place back. I take and I put back. Sorry, give me a moment over here. Find a worry that at the end of the experiment, box A has more yellow balls than blue balls. Okay. Is it right that we stop here? What are your thoughts? Stop here, right? Sorry, please give me a chance to rethink. Sometimes I prepare something, then after that in class I will think something else, then after that I will confuse myself. More yellow than blue. Exactly 7. At the end of the experiment, box A has exactly 7 blue and 5 yellow. Exactly 7 blue and 5 yellow. Okay. Yeah, okay, so we will keep it to this now. Okay, so we are taking from box A to box B, this will be probability, and this one is the one from taking from B to A. Okay, then we stop here. Right? So let's look at the questions now. Okay, in B part I, we want to find the probability that there are more yellow balls than blue balls. Okay, at the end of that box A, okay, has more yellow balls than blue balls. Okay, we are solely looking at box A, right? Box A started off with 7 blue and 5 yellow. Will there be a case where they end up having more yellow than blue? No, right? Okay, because if you started off even taking a blue one, okay, which will reduce it by 1, and then after that, even if you replace it with a yellow one, okay, end up I will only have 6 and 6. Okay, so that's the closest that we can get in terms of trying to increase the number of yellow and reducing the number of blue, right? So therefore, there is no chance then there will be more yellow than blue. Okay, then in part 2, we want to find the probability that box A has exactly 7 blue and 5 yellow. Okay, what would the cases be that we have to consider? If we want to have exactly 7 blue and 5 yellow. If I had taken a blue at first out from box A to put it into box B, what do I need to do to ensure that I still have 7 blue and 5 yellow at the end? What do you think? Zhen Quan? If I took out a blue one from box A and I put it into box B, but I want to actually maintain 7 blue and 5 yellow at the very end of the day, okay, what must I be taking out from box B to put back into A if I first took out a blue? You understand my question? So what would answer be? I take one blue one out from A, put it into B. I want to take something out from B, put it back into A, so that I still have 7 blue and 5 yellow. Sorry? 7 over 12 times 4 out of 11. So as long as I take out one blue, okay, I need to return the blue back from B itself. So therefore it must be a blue-blue combination. Otherwise, if I had taken out a yellow, okay, then I must put back the yellow so that I can have 7 blue and 5 yellow at the very end. Okay, so we are looking at a blue-blue combination and a yellow-yellow combination. Okay, and that would leave us with 17 over 33. Okay, last one. How should I go about shifting the balls such that at the end in box A there are 2 times more blue than yellow? Currently we have 7 blue and 5 yellow. So what must we do? What should I take out from box A first, and what should I put back into box A after that? What do you think, Joseph? What must I take out from box A? And what must I put back into box A in order to have 2 times more blue than yellow? 5 over 12 times 3 over 11. So if I were to take out 1 yellow, I'm down to 4 yellow. And then I put in 1 blue, I will get 8 blue. So 8 is 2 times of 4. Okay, so we are looking at yellow and blue. Alright, so 5 over 12 times 3 over 11. Okay, and we have 5 over 44 over here. Is that the only possibility? Yes, right? Because if I had taken out the blue, I'll be left with 6 blue. Right? In order to have 6 blue and 3 yellow, that's not possible because I currently have 5 yellow and I'm not going to take out anything from the box A anymore. Okay, so this will be the only combination. Okay, any questions? Right? Yeah? what I was stuck with right just now, okay, was that I wanted to continue drawing. Okay, whereby this third column is about taking from box A. But there's no part in the question that talks about having to take a ball out of box A. Because if you look at part B, all the questions, okay, was asking about how many balls do we have left at the very end. Am I right to say? Okay, how many balls do we have left at the end in the box A itself? Okay, so if I draw this part, okay, this column over here, it is going to talk about taking from box A. And if I put in the numbers, so let's say, okay, I take one from blue, one from A, blue, and then after I put back a blue, I will still be left with 7 blue in the box, so 7 out of 12. Am I right? Yep. Okay, because I take one from A, put it back, okay, put it into B, and then I take one from B, and then put it back. So I know that there are 7 blue in the end, out of a total of 12. And then in my yellow, I will have 5 out of 12. If you do it for the rest of the column, okay, if you do it for the rest of it, it will be an easy, okay, deal for you to compare to know how many blue and how many yellow are there inside box A at the very end of the day. Right? Because if you want to answer the question about what is the case having more yellow than blue, if you just look at the numbers of the numerator, more yellow than blue, that's not possible. Okay, that's why we know that it's 0. Whereas in part 2, box A has exactly 7 blue and 5 yellow. Okay, then we will see 7 blue, 5 yellow, 7 blue, 5 yellow. Right, so we're looking at these two, and how do we arrive at these two? We are looking at 7 over 12 times 4 over 11, 5 over 12 times 8 over 11. I'm not going to continue multiplying these numbers. Okay, although you can, because the numbers will still, because these two, as long as they add up, they will become 1. Okay, so it doesn't quite affect the answer at all. You understand what I'm saying? Okay. Then in my third part, you have twice as many blue and yellow. Okay. If I were to just look at the numerators, I know that this is the only possibility, and that comes when 5 over 12 times 3 over 11. You can take 5 over 12 times 3 over 11 times 8 over 12. Then you plus 5 over 12 times 3 over 11 times 4 over 12. Answer will still be the same as 5 over 12 times 3 over 11. You understand what I'm saying? Okay, so having to write down this third column is just an easy way for you to see, okay, what are the numbers in box A at the very end. Okay, but you need not have this to illustrate the situation that has been given to you. Okay, are we all good? Any questions? Go on. Let's look at question 19. rolling a die, okay, the game will actually stop when you roll a 6. Okay? In A part I, we want to look at the game ending on the 3rd row. Part 2, we are looking at ending on the 4th row. And part 3, we end by the 4th row. Okay? So this is a test of your English understanding as well, okay, to see how you count. Let's do part I and part 2 first, okay, where we want to end the game on the 3rd row. What this means is that we will be getting the number 6 on the 3rd row itself. Okay? If you want to draw a tree diagram, there's no need for you to go and draw 1, 2, 3, 4, 5, 6. Okay? That will be very tedious. Okay? Why is it that we need not draw that? Because in this question, it is about getting a 6 or not 6. That's all. Okay? They are not concerned about getting any other number than 6. Okay? So to simplify your tree diagram, if you were to draw one, okay, it will either be not 6 or getting a 6. Okay? And the probability is 5/6 and 1/6. So this will be in your first row. Okay? Then on the second row, because it's not 6, so we can continue. Okay? So then we will get not 6 and 6. They are independent events because your first row doesn't affect your second row. Okay? So I will get 5/6 and 1/6 for not 6 and 6. Do I continue after this if I were to choose a 6? If I were to get a 6 over here? Is there any continuation? No, right? Because the game will end here. Okay? So technically your tree diagram has no continuation from the 6s itself. Okay? Then you can continue. Not 6 and 6. Okay? This tree diagram continues on infinitely, right? All the way until you get a 6. Okay? In this question, they did not ask for a tree diagram, okay, because it's not physically possible to draw such a tree diagram. Okay? So this tree diagram over here is for us to understand what the question is asking, so that it will facilitate our calculation later on. So in part I, for the game to end on the 3rd row, okay, that means that my first row I must not get a 6, second row I must not get a 6, 3rd row then I get a 6. Oh sorry, this is 1/6, right? Okay, so my probability will be 5/6 times 5/6 times 1/6. Okay. And in part 2, what would the probability be then if I want to end on the 4th row? What do you think the probability will be? 125 over? If you can give me 6 times 6 times 6 times 6, and the calculation, I'll be very amazed. Okay, how do you get that? I'm not talking about how do you get 1,296. How do you get this fraction here?
5/6 times 5/6 times 5/6 times 1/6.
Yes. Okay, so we are continuously looking at not being able to get a 6. Then finally we get a 6. So 5/6 3 times or 3 rows. On the 4th row, then we get 1/6. So that is not illustrated in my tree diagram over here. You will have to continue one more set. Okay, so this tree diagram is just for us to get an idea. Right? Next, part 3. Okay, we want the game to end by the 4th row. What does by the 4th row means? So it can end on the first row, it can end on the second row, it can end on the third row, or it can end on the fourth row. So there are many cases for us to consider. Okay, so if you want to, okay, you could think of on the first row will just be 1/6. Then you plus. On the second row, we will get 5/6 times 1/6. Then on the third row, oops, and then on the fourth row, okay. In this case, you will get 671 over 1296. Is there an alternative to answering this question? Yes, Dylan. Okay, yes, very good. So another way that you can say is 1 minus probability that it does not end, okay, by fourth row. Okay, and that will actually mean that it never ends, so not 6, not 6, not 6, not 6. And that will be 1 minus 5/6 times 5/6 times 5/6 times 5/6. You would still get the same answer, which is 671 over 1296. Okay, and that is an important thing to actually learn as well. Because if I had asked you for the game to end on by the maybe 20th row, okay, then it will definitely be very difficult for you to consider all the cases. By the time you reach the 20th one, you will have to start counting how many 5/6 you're writing. But of course, you can write index notation. Yes. Is it possible what? Find the probability that rolling two numbers consecutively. So we have to consider one at a time. No? Yeah, independent. Yeah. There is a possibility. Depends on the question. I can't imagine how the question will be set at this moment. Yeah, you can go and try it. Then we can test it out. Okay, next we look at part B. Suppose that now that the game is such that the same die is rolled repeatedly until 2 6 are obtained. Find the probability that it ends on the third row. Okay, so we want 2 6. Probability will be if the game ends on the third row. Okay, it will only end when 2 6 are obtained. Okay, we want it to end on the third row. So for the first row, should there be any 6? No, right? So that we can continue to the second row, right? Okay, so if there's not 6, then after on our second row, I will get a 6. On the third row, I must also get a 6. Then it will end. Right? But did the question say that the 2 6 must be consecutive? No, right? So one case that we can look at, oops, sorry, should I use the blue one? Is to have first row not 6, then 6, then 6. Okay, although this tree diagram doesn't fully illustrate it. Okay, otherwise you can have first row 6, then not 6, then 6 again. That's also a possibility. Can I have 6, 6 and not 6? No. Okay, why? Because it will end on the second row already, instead of ending on the third row as per what the question wants. So our cases to consider would be probability of not 6, 6 and 6 plus probability of 6, not 6 and 6. So 5 over 6 times 1 over 6 times 1 over 6. 1 over 6 times 5 over 6 times 1 over 6. And that will be our 5 over 100. Okay. Part 2. We want the game to end on the third row, and with the condition that the sum of the scores is odd. So what kind of combination are we looking at? We need to then split up to think about our not 6 already. Okay, so let's just list it in a so-called coordinate kind of form. Okay, I want it, so having to end on the third row, the cases are this or this, right? Okay, so let's explore this first case first. To have not 6, what kind of numbers could I have? Because the second and the third will actually be 6, right? So what kind of number must I have over here such that the sum of these numbers is going to be odd number? What must I have, Teresa? 1, 3, 5. Okay, so we can have 1, 3, or 5. We cannot have an even number because 6 and 6 add together is already even. Even number plus even number surely is even. You add another even number, it will also be even. Okay, so Shen, would you like to go and wash your face? Right? Then, therefore, you should only be choosing the odd numbers. Okay, so these are the 3 cases that fall out of this one. Then we need to consider the next 3 cases for 6, not 6 and 6. So it's just the other way round, where we have 6, 1, 6, 6, 3, 6, and 6, 5, 6. This is where you list out all the different combinations and consider them. Okay? And the probability of getting each of these numbers is always 1 over 6. So one pair or one set over here will be 1 over 6 times 1 over 6 times 1 over 6. So it is 1 over 6 to the power of 3 now. Okay? And there are 1, 2, 3, 4, 5, 6. All of them actually have the same probability. Do you see that? Okay, they all have the same probability. So I can just times 6. Because 6 times of the same probability. Right? Because it is 1 over 6 to the power of 3 plus 1 over 6 to the power of 3 plus 1 over 6 to the power of 3 plus 1 over 6 to the power of 3 plus 1 over 6 to the power of 3 and plus 1 over 6 to the power of 3. Yes, Dylan?
I mean, that's replace 5 over 6 to the power.
5 over 6. This one, yes, you can. That's another way that you can count as well. Because 1, 3, 5, those are odd numbers. On the die itself, half are odd, half are even. You can also consider half times 1 over 6 times 1 over 6 plus 1 over 6 times half times 1 over 6. Okay? Now when it comes to probability, okay, this is where counting is very important. Okay? And you'll probably realize you don't know how to count anymore. Okay? That's what I learned at the end of my university days. At the end of university, I forgot how to count. Yeah, because probability confuses you. Right? So there are many ways that you can go about thinking it. Okay? One way is what Dylan said. Think of half. Half is odd. Then times 1 over 6 times 1 over 6 for the 6s. And then consider the other option. Or you can really list it out so that you can be careful about it. Okay? If you can't imagine this, really there is no issue at all. if you want to just do case by case. And you write it 6 times. Okay, I'll just save the time, not writing. But essentially you write it 6 times. Okay, and you will get your answer to be 1/36. Okay, any question? Right, probability you really got to read the question, understand the question carefully, okay, and consider all the cases that are possible. There was one here, okay, I think for prelim or for me exam, I forgot, okay, it was about number of socks, okay. So question was on the pair of socks, okay. I remember I said it I said it when 4 years ago, yeah. So the question says 1 pair of socks, 2 pair of socks. Socks come in pairs, right? Okay, 1 and 2. But then in the end, when you choose a sock, okay, they are talking about choosing 1 sock at a time instead of pairs. Okay, yeah. So it affected many students' probabilities in the tree diagram itself. I'll go and find a question. I'll show it to you another time. Huh? What? Why does it matter? You don't do then never mind. Yeah. You taking exam but not taking exam but just giving it to you for your benefit, right? Then you ask this for no reason, then don't ask. Do you have a rock over there? Okay, so that's it for chapter 2. I am going to give you this set of notes for chapter 3. The reason why I printed notes is because I find that it's easier for you to draw onto diagrams. 2, 3, 4, 5, 6, 7, 8, 9. What's that? Is it somebody's glasses? 2, 3, 4, 5. You don't have to submit, haven't completed your homework, you must submit. Yes. Okay, because I'm going to print worksheets for you and then also past year papers for you subsequently for your mid-year exam and maybe at to the end of the year. Okay, could I request that we have a class fund? Last year we had class fund, okay, if you remember. Remember, you all gave me $2. I still kept it. Okay, I still keep accounting of it. Alright, I can show you all the accounts. So I use part of that money. Okay, in fact, we are on negative now to print this set of worksheets today. Okay, you all gave me $2 last year, and we printed some last year also. Okay, then this year, could I request that you put $4 each into the class fund? If there is any remainder, okay, of course I'll return it to you. Okay, if end up the net is only a few cents in the end, I'll just top up and I'll just return it to you. Okay, can? So could I please collect it tomorrow? Would that be okay? $4. Yeah. Okay. If you have issues regarding that matter, please come and talk to me. Okay, we can see what we can work out. Alright? Okay. Let's start on our chapter 3. We only got 10 minutes. I'll just do page 1. statistics. Okay, we are going to look at cumulative frequency. As the word cumulative suggests, it means that the root word is cumulative, okay, accumulate, so to add up. Okay, so that's the meaning of cumulative, which is to add things up. So what exactly are we going to be adding up? We're going to be adding up the number of data that we have. Okay, because cumulative frequency is the number of data that we have. Right? In set 1 and 2, okay, that was the last touch point that we had for statistics. We learned different kinds of diagrams, dot diagrams, step and leaf histograms. Okay? In this year, we are going to learn a newer form of diagram, which is the cumulative frequency curve, okay, as well as box and whisker plots, okay, which looks like this. Okay? So, let's try to understand the cumulative frequency table that is needed for a cumulative frequency curve. Okay? Take note that you are not required to plot a cumulative frequency curve in your syllabus. So the graph will always be given to you. Okay? You don't usually have to draw it out. Okay? Table 1 shows the frequency table for the number of hours spent by 40 students surfing the internet on a particular day. So they went to do a survey and this is the results of it. So what this result tells us is that there are 3 students, which is the frequency, that spend 0 to 2 hours, okay, on the internet. And then over here, there are 12 students that spend 6 to 8 hours on the internet. Table 2, okay, is for the corresponding table for the cumulative frequencies. So you notice that in table 2 itself, okay, in this case we have t less than or equals to 2, while over here we have a range of 0 to 2. So if I want t less than or equals to 2, that means from 2 downwards, okay, how many students are there? Since it only goes up to 0, okay, so our answer will be 3. While in the second row, we want t less than or equals to 4. That means from 4 all the way to 0, how many students are there? We have 5 and 3, so 3 plus 5 equals to 8. That is the idea of cumulative that we're having. Next one, okay, we want t less than or equals to 6. Okay, and that will be reading from the frequency table. We have 16 plus 5 plus 3. Okay, which will be equals to 24. Alternatively, you can also think of it as 16 plus 8. Then in the next row, we have t less than or equals to 8 and t less than or equals to 10. So less than or equals to 8 will be 12, 16, 5 and 3. Okay, and that will give us 36. And lastly, we have 40. Okay, if I were to add up the 4 as well. Okay, question 2. Using your answers in table 2, we want to find the number of students who surf the internet for 6 hours or less. Okay, so this is a frequency table. While this is a cumulative frequency table. In cumulative frequency, we are always talking about the data that is in the form of less than or equals to. Okay, we do not present data that is more than or equals to. Okay, that is the standard that we seek in cumulative frequency. So, using table 2 to find out 6 hours or less, and that will be over here, because 6 hours lesser than or equals to, that will be 24 students. Now what if I want more than 8 hours? Okay, in this case we can't get the more than directly by reading. We acknowledge that there are 36 students that spend less than or equals to 8, but there is a total of 40 students as given in the question. So I need to consider 40 minus 36. That will be equals to 4. So there are 4 students that spend more than 8 hours. Okay? I want more than 4 hours, but not more than 8 hours. Okay, so that means I'm seeking for in between 4 and 8 hours. Okay, 4 hours, I have 8 students that spend lesser than or equals to 4. 8 hours, I was spending lesser than or equals to 8 hours, I have 36 students. To get the in between, I take 36 minus away 8. Okay, so this will be what it means, in between. Okay, these are common questions to be asked, not really for cumulative frequency table, but for cumulative frequency curve. Okay, because that's most of the time that's what. Okay, something to take note of in your cumulative frequency table is that this last number that you find is always representative of the total number of students. Because you're basically adding up every single student found in the frequency, so at the very end, it should always be the total number of students. Other words, to be more general, okay, it is a total frequency. Okay, I'll just end here today. Tomorrow we will continue with this. So please make sure that you bring this set of notes for all your lessons for chapter 3.